Hi, I'm Prof. I'm a professor at the University of Applied Sciences in Kempten, and this is part of my lecture on measurement technology. Today, talking about some sensor technology about temperature sensors. We already got to know one way of measuring the temperature, and that's the way of using ohmic resistor. Any ohmic resistor out there changes its resistance due to the temperature. Even copper wires drastically change their resistance due to the temperature. We know that normally there are those platinum wires, those platinum resistors, which are used for measuring the temperature. And we already know that we get a very nice behavior of that resistance, which is somehow directly proportional to the temperature, or let's say to something like a polynomial form of the temperature. The direct proportional behavior absolutely dominates the behavior, the connection of the resistance to the temperature. But we know the corrections, which are not linear, which are not direct proportional. So fine, we know a way of measuring the temperature. Now, why talking about another way of measuring the temperature? Good question. And the answer is, we have to heat up the whole resistor to get an idea of the temperature of the resistor. So heating up 100 ohms of platinum wire needs some time. It's not working instantly. It takes seconds, perhaps minutes, depending on the resistor we have over here. You can just imagine a little resistor and you have to heat it all the way. So, for sure, the known system is not very dynamically. But for some applications in industries, especially in the process industries, we need to have some more rapid way of measuring the temperature. And for those more rapid ways, thermocouples come into play. What is a thermocouple? The idea is quite simple. We have two materials. Let's paint it in the other direction. You have two materials, A and B, which are connected in a point, and by that exert a thermal voltage. So imagine we have some temperature over here, and we have some reference temperature over here. For example, 0 degrees Celsius. Now, when those two wires contact at that heated place over here, the electrons will drift away from the tips, from the place where the heat is exerted. That place is very small, and it will heat up, it will get heated up very fast. So we don't have the dynamic problems, and those electrons will react very fast also. By the fact, or due to the fact that we have a material A and a material B, that drift of the electrons will be different in both materials. And now we get the idea why a voltage is exerted when a temperature is applied over here. That is heavily dependent on the choice of materials, for sure. And that's the reason why normally when you want to know how to use a thermocouple, you go into tables where those voltages are marked in millivolt per 100 Kelvin. That's the reason for the 100 degrees over there, in combination with a material B of platinum. So now for a material A of, for example, let's take iron, we get 1.9 volts per millivolts per 100 Kelvin as a reaction constant. For sure, when material A would be platinum itself again, we would get 0 millivolts. Because it's the same material, no difference in the reaction of the electrons is there, so we get no voltage. And this goes on and on and on for different types of materials. Now, whenever we combine two materials A and B, which are not relative to platinum, for example, let's combine nickel chrome to nickel. Actually, we can take the constants out of our table. Those are denoted. And for example, for nickel, we get minus 1.9. And for nickel chromium, we get 2.2. And now when we want to know that constant K, we have denoted here for that material combination, we can just use those relative combinations to platinum. So those are the values relative to platinum. To get the value of nickel chrome relative to nickel, we just subtract the two constants, minus 1.9, giving us 4.1 millivolts per 100 Kelvin. Yeah, we need that over here too. Okay, great. Now we know what voltage is exerted. How do we know that? We know that by setting up a measurement with two different materials. And now let's sketch that setup. So we have the two materials. Over here we have our temperature we want to know about, the measurement temperature. We have the two materials A and B over here. And now normally we would measure that voltage which is exerted by the thermocouple by connecting it via, for example, copper cables to a voltage meter. So you see we get another pair of materials over here. Copper and material B and copper and material A. So we have several material combinations over here. And for that reason, the temperature, the reference temperature, TV, gets important. Now, in this way, combining, for K times T will give you some voltage over here. And now combining those voltages together and doing the overall calculation for the measured voltage over here, we get the constant of material A and B, as we denoted it here, times the measurement temperature minus the reference point temperature. As you see, we can use that correlation to get some hold on the temperatures over here. We have one problem. That temperature of our reference point. We have to know it. That's a fact. I cannot tell you any simple solution for that. We have to know that reference temperature in order to know the measurement temperature which we want to know about. What is the resolution of this problem? This is the thing we want to know about. No problem to measure the voltage and to use the constant to get the measurement temperature as long as we know that reference point temperature. But how to get that reference point temperature? Yeah, we have to use something like a platinum wire, platinum 100 resistor to measure that temperature. Why is that still an improvement somehow, or some where are the benefits compared to just using a PT100 resistor temperature sensor? Simple said, we know those tips are very dynamically. It's a small amount of material which can be heated up very fast. So the sensor, the exerted thermal voltage reacts very fast to changes in the temperature. And we know that reference point temperature, we are in control of that. Imagine your voltage meter and you plug in the device there. You can very exactly, or you can just try to control that reference point temperature very exactly. More important, that reference point temperature is not exerted to drastic changes in temperature. So it will remain its temperature over a long time. So we don't have the dynamic problem for measuring the reference temperature. And that's the reason why it's very legitimate to just use a PT100 resistor to measure that reference temperature. So, having done so, we now have the possibility to do a dynamical temperature measurement using those thermocouples. One fact about the thermocouples, which is somehow interesting, is that kind of the best thermocouples still have an accuracy of plus minus 1 degree Celsius or Kelvin when measuring absolute temperatures. That's an important thing for measuring the absolute temperatures. For relative changes, we have better accuracies. So the change in temperature is much more accurate for those thermocouples than the absolute temperature. The reason for that, those bad accuracies for the absolute temperature are obvious. Yeah, you know we have some connection points over here. We have to measure that reference point temperature, and all that brings in some more errors we have to deal with, increasing the absolute error for the absolute temperature. Still, the change of all of that stuff thus is not harmed by all of those errors, because those errors are somewhat constant. We have connected it. One time we have clamped the wires, and now we have some absolute error for the reason of clamping those wires and so on. But that absolute error will remain constant, and for that reason, that relative error in measuring the measurement temperature over here is not that big compared to the absolute temperature error. Altogether, still very usable and still used for the explained reasons for dynamic temperature measurements. Okay, I hope you liked that stuff. See you next time.